Hello everyone, my name is Lorenzzo Mantovani and I will present the paper Improving Robustness of Autonomous Spacecraft Scheduling Using Curriculum Learning. First, talking about the satellite scheduling problem. Traditionally, spacecraft tasking was performed by human operators or optimization algorithms. The problem with optimization algorithms is that although sometimes they have optimality guarantees, they can be brittle to initial condition changes and expensive to run on board. On the other hand, we can use deep reinforcement learning that allows for onboard closed-loop decision making and can get solutions close to optimal, but brings some safety concerns. These safety concerns from deep reinforcement learning policies are associated, for example, if satellites are deployed in an environment that are different from that environment they were trained on. Something else is if you use shorter truncated episodes during training, it doesn't really mimic the long-term deployment you have in real life where satellites are in orbit for months and years. It intensifies if you're working, for example, with a constellation of satellites. Even if they are identical, they are not really identical. They will have differences in their parameters and they will degrade in different ways over time. So if you have a policy that is robust, you can use the same policy for all the satellites in your constellation and it will perform well. So how can we shape the training environment to increase the policy robustness? In previous work, we look at how can we enhance this training environment, and we consider some fixed enhancement levels. But there's another methodology that we can look at that is curriculum learning, and it's a way to shape training environments to improve learning. It provides a structured change in difficulty over time. So in this work, we want to look at how can we use curriculum learning to improve the robustness of DRL-based policies for spacecraft tasking. Talking now about the decision-making problem and simulation environment. In here, we are considering an Earth observing satellite that has four actions. One of them is nadir scanning mode. We also have downlink mode, charging mode, and desaturation mode for the reaction wheels. We can formulate the problem using a partially observable Markov decision process where we have a state space that contains information about satellite, environment, and internal states to the simulator. Also, we have an observation space that contains information useful for decision making. As I mentioned before, we have four actions: nadir scan, charge, downlink, and reaction wheel momentum management. Some constraints that we are considering are that the satellite should keep a positive battery level at all times, and also the reaction wheels should not exceed a threshold, their angular velocity. If these constraints are not met, the satellite reaches a terminal state, so it's a failure. The reward function we consider is the amount of time the satellite spends imaging nadir, and it's normalized by the episode length, so the maximum reward you can get is 1. Given this formulation, we can find a policy that maximizes the sum of the expected cumulative rewards, and we can find this policy using deep reinforcement learning. A policy will map states to actions, allowing closed-loop decision-making, and we are using the APPO algorithm, which is the asynchronous proximal policy optimization algorithm. The advantages are that we can include complex dynamics and constraints, and it's fast to evaluate after training. Among the disadvantages, we have the training cost that can take some hours. We implemented the simulation environment in BSKRL, which combines Basilisk with Gymnasium. Gymnasium is a standard interface for reinforcement learning studies, and Basilisk is a spacecraft astrodynamics simulation software. It has flight-proven software, modular configuration, and it's fast, which makes it an ideal software to be used in reinforcement learning. So how can we enhance the training environment? We looked at 3 different ways to enhance. The main one is curriculum learning. We considered 3 different curriculum structures that I will talk more later. In this curriculum, we consider adding only battery capacity variation and also battery capacity and external torque variation. We looked also at extending the length of the episodes during training. So instead of using 3 orbits truncated episodes, we were considering also 15 orbits, so longer episodes. In addition to that, we are also looking at the randomization range. So every time you reset your environment during training, you randomize some of its initial conditions, so you expose the agent to a more diverse scenario. And here in the narrow initialization, looking at the safety aspects, we were initializing the battery fraction and the reaction wheel speeds to a nominal range, while in the wider initialization, you can think of it as varying from the minimum to the maximum values they can reach. So for each of the combinations in curriculum learning, episode length, and randomization range, we trained three policies to average out any random results we could get during training. So this resulted in 114 policies. So talking more about curriculum learning, it's a methodology to shape the training using a structured sequence. And in this case, we are changing the difficulty over training as a function of the number of steps. And we tested three different curriculums. The direct one is shown in blue. It's an increasing difficulty, so it starts at 1 and go towards 1.5. The constant one is just constant across the training, and the inverse starts at a harder level and then it decreases and go towards the nominal. The idea here behind the direct curriculum is to expose the agent to the nominal environment first, and over time, as it gets more difficult, it would learn how to handle safety aspects of the problem better. The inverse curriculum is the opposite, where you are exposing the agent to a harder environment from the beginning, where it is incentivized to learn more the safety aspects first and later on optimize for rewards as environment gets easier. Usually the curriculum learning starts in a difficulty lower than 1, and 1 is the end point of the curriculum, but here we are interested in cases where the satellite would have degraded capabilities. So we are looking at cases with a higher difficulty. Additionally, we also consider a domain randomization case where it doesn't follow a structured sequence over training, it's just randomly sampling a difficulty and training the agent at that difficulty. And it was used as comparison. In addition to the curriculum structure, we also need to define the intensity of that curriculum. And we are varying two things, battery capacity and external torque. So initially, we just varied battery capacity and three levels, decreasing 20%, 40%, and 60%. And we also combined it with external torque's variation. And the reason for us to include external torque is if you have external torque, your reaction wheels will start to get increase their momentum, and it basically means higher speeds, and it will draw more power from the battery, so it will also affect how you are handling power. So going to the results section, as I mentioned, the policies were trained in two different environments and with respect to episode lengths, 3 orbits and about 15 orbits, but they were also tested at 71 orbits and about 350 orbits because we wanted to see what would happen to the agent if it's exposed to much longer episodes, as would happen in reality. In addition to that, we consider two versions of the environment for testing. We consider a nominal case and a degraded case, with decreased battery capacity, increased external torque, and decreased solar panel efficiency. When we combine all these test cases, it leads to almost 3,000 years of simulation time. Still, I'm just going to show you the cases with 350 orbits and the degraded environment because the differences in curriculums are more visible, but you can refer to the paper for a more detailed discussion. So talking about results, first I'm going to talk about single satellite results where we try to answer some more fundamental questions as what should we vary with our curriculum, should we use shorter or longer episodes, and should we use the narrow or wide initialization range. Then I'm gonna show a multi-satellite example where we have 5 different satellites with different parameters running the same policy. So first, what should we include in the curriculum? Here we have results comparing the baseline policy, the gray bar, and cases trained with the direct curriculum. So the first 3 blue bars, they were trained using only battery capacity variations, but with different intensities. The last 3 bars, they included battery capacity and external torque variation in their curriculum. And what we notice here is that the height of those bars are lower for the 3 last policies when comparing the same intensities, indicating that when we are including external torque in the curriculum, we are getting less failures. More interestingly here is that you notice that we have less failures associated with reaction wheels that are indicated by circles in there. So from now on, we are gonna keep using cases that were trained with both battery capacity and external torque variation in the curriculum. Next, should we use short or longer episodes? So on the left, we have results using 3-orbit long episodes, the shorter episodes, and on the right, we have using the 15-orbit long episodes. And the first thing we notice if we look at failure percentage is that the bars on the right tend to be lower than those bars on the left, indicating that extending the length of these training episodes is beneficial, reducing the number of failures. Additionally, if we look at the cumulative rewards, the top two plots, we notice that the cumulative rewards on the right, they tend to be more concentrated towards the top compared to the plots on the left, indicating that more cases are getting higher rewards. Lastly, we have the comparison between narrow or wide initialization ranges. And here on the left, we have narrow initialization, where we randomize the initial battery fraction and initial reaction wheel speeds in the nominal range. And on the right, we have the wide initialization, where we vary that from the minimum to the maximum values they can get. What we notice, again, we have less failures when we're using a wide initialization. However, here, if we look at cumulative reward, we notice that some cases start to have a decrease in cumulative reward, indicating that these policies are becoming overly conservative. They are reducing failures, but also reducing the cumulative reward we are getting. So when we are combining some of these curriculum intensities with wide initialization, the environment might be becoming too difficult for the policy, for the agent to learn. Still, if we look at the gray bar, that's the baseline that didn't use any kind of curriculum, we see a significant decrease in failures comparing the wide to the narrow initialization and also higher cumulative reward. So what does that mean for a multi-satellite example? If you think about a constellation of what could be identical satellites, they will still have differences, and over time they will have different degradations. You can think about different battery capacities over time or different solar panel efficiencies and so on. So in this case, we consider 5 different satellites. Each of the satellites has different parameters, and the last one, the EO4 here, has parameters that are varying over time just to simulate some degradation over time. And we selected the best baseline policy that was trained without any curriculum, but was trained using longer episodes and wide initialization. And we compared to the case that was trained with the direct curriculum using longer episodes and narrow initialization. And here are the results. We have the reward and failure percentage. And the first thing we notice here is that the bars for failure percentage are showing a lot less failures for the blue policy, that is the one trained with curriculum across all satellites, indicating it to be more robust. The only case where we have less failures with the baseline policy is for the first satellite, the EO0, because this satellite represents the nominal environment in which the baseline policy was trained on during the whole training. So it is expected, but when we start to deviate from that, it shows a lot more failures, indicating that we are benefiting from this robust policy. Some concluding remarks. This work intended to investigate how using a structured training could enhance the robustness of DRL-based policies for spacecraft tasking. What we found is that the direct and constant curriculums showed the best performance, and that adding both battery and torque were beneficial, reducing failures, and also using those long episodes was better than using shorter episodes. Still, wide initialization was mostly beneficial when you are not using any kind of curriculum. And we also showed a case demonstrating its applicability to a multi-satellite case. And future work would include adding more information to the agent, so it could know, for example, the level of degradation of the battery and have a more informed decision making and take advantage of that. Thank you for your attention.